So today we're going to do Bode plots of active circuits. That means an op-amp. And I want to try a breakout room with a review activity. So the first thing, it's called the Howland current pump. You would have seen it in the lab manual. Hey, Nick, I'm not quite sure what you mean. No, it was last week. I just didn't call it the Howland current pump. So the Howland current pump uses negative feedback, where we have a current coming back from V out and through voltage division affects this V in negative. But we also have a positive feedback, and it can be a little bit difficult to understand or a little bit difficult to derive it if you don't recognize certain things. All right. And so the first thing to recognize, right, is that this is non-inverting. And in this circuit, we set these two resistances equal to each other, so we get a gain of 2. So that's kind of important, right? And I didn't say it, but when I'm trying to figure out what an op-amp circuit does, first thing I do is assume that it's ideal, all right? And so if I just label this node Vx, right, V out equals 2Vx. Now, we've got this V out coming here, and so even though I normally try to use voltage division wherever I can, this time I'm going to use nodal analysis. So I'm saying the current is coming in here, it's coming in that node, and it's leaving through that resistor. We put our positives and our minuses, right? And then we write our nodal equation, and that IR3 plus IR4. And even myself, when I'm doing this, sometimes I'm so used to going from left to right that I forget the current is coming into the node, and I put that on the wrong side. and then current coming through the impedance. All right. Then, I substitute these nodal voltages and resistances. So we have Vn minus, Vx R3 plus V out minus Vx R4 equals Vx divided by Z. We're going to substitute that, and we're going to have these two resistances equal to each other. So we get Vn R3 minus Vx R3 plus 2Vx minus Vx R3 equals Vx divided by the impedance. Well, we can see that that becomes minus Vx R3, plus, that's what I meant to say, which then cancels each other out here. And that means that all right, so we have an impedance scale by resistance, so the units match. And then we take this and substitute it here, right? And we get V out equals 2. And let's put it in terms of a transfer function. All right. Now, Z, right? ZL equals S times L. SC equals 1 over SC. And this circuit in general is used with a capacitor. So we're going to get 2 R3 C S, which is an integrator. So if we substitute some values into that transfer equation, we get 1 over S. All right. And there's no simplification on this, right? It's real all the time. And S equals J omega all the time. So there isn't going to be any bends in this circuit because these relationships will always hold. So for the magnitude, right, we have the magnitude of the numerator divided by the magnitude of the denominator. Right? This is all real, there's no imaginary. And in the denominator, it's all an imaginary component. So we have 1 over omega. I'm going to just put start up here. So we have 20 log 1 over omega, which then becomes minus 20 log of omega. Since we're plotting on a logarithmic by decade scale, right? Every time we go a decade, we are going to go down minus 20 dB. And it'll be 0 dB when omega equals 1. Okay, so I just to guide myself, right, I put a dot there. And then I go up 20 over 10, up 20 over 10, so I know I can start here. And then, to the best of my ability, draw a line. Like that. And, oops, I can try to highlight that. All right. So the phase, right, we're going to have the phase of the numerator, phase of the denominator, and we don't, which is we don't really care about these magnitudes because we've already done that. We really care about the phase angles here, right? But looking back here, we can see it's real the whole time, right? That means we have a vector pointing that way, which means it's 0 degrees. And then here, right, it was all imaginary, right? So that's 90 degrees, which when we take and convert, you know, the magnitudes are 1 divided by the other, but then the phases are subtracted, so it's minus 90 everywhere. All right, so I just have to come down to 90. Right, it's constant everywhere. And there we have it, okay? So that would be the integrator, right? If it were the inverting integrator, right? Magnitude wouldn't change, but the phase would start off at minus 180. Okay. Or actually, it's really plus 180. Because when you take 180 minus 90, the phase would become 90. And that's what LT-Spice and the Python packages will do. So you probably just have to know that minus 1 becomes 180. All right, so we have two stages here, right? Just looking at it, right? This is an inverting stage, and this is an inverting stage. All right, and this circuit here really becomes what I'm trying to draw right now. All right, and again, we're going to assume that everything's ideal. Now, the gain of an inverting op-amp configuration is given as this, right? But now G's are just gain and they don't have a frequency component. We're going to use H, and things that have frequency components are impedances, all right? And so we're going to have Z C1 in parallel with Z R2 divided by Z R1. All right. And this is for stage one. ZR2 is R2. ZC is 1 over SC1, R2 plus. All right. Now you want to get this into a proper format that you can understand. So you multiply this S through, all right, and you get S R2 plus 1 over C1. And then you pull out an R2. And that might seem a little counterintuitive. All right. Now it's easier to put these things in terms of omega naught or the break frequency, which in this case radians per second. All right. So HS1 is going to be R2 omega naught S plus omega naught. Now that we have 1, we can get the total just by multiplying them together. Yep, 1 kiloradian per second. I'm writing some certain things down, and then I'm just going to go back and explain. All right. So C1 is equal to C2, R2 and R4 are equal, and R1 and R3 are equal, and equal to these values that I set here. So that when I find HS of 1, right, I get a gain of 10, and omega naught is 1,000. That means HS2 is the same thing. And ultimately, we get this transfer function here. So to come back in the parallel combination, okay. Right, so we get ZR2, ZC1, ZR2 plus divided by the sum of that. You have R2, and then this is 1 over SC1. Then you have the sum of the impedances. All right. So I factor out R2, but I don't cancel them because it'll just make things more difficult. I keep the C1 factored out, and I multiply through by S. Okay, which that value there is R2 C1, and so you get R omega naught S divided by omega naught. Okay. Okay, well, I think I went back and did this. Okay. All right, I'm getting a thanks. Okay, good. Okay, yep. All right, so now I'm just gonna We had a gain of 100. We had omega naught squared. We had 2 repeated roots, poles at 1 kiloradian per second. All right. So there's 2 poles, but they're repeated. So really, we just have when omega is less than 1K and when omega is greater than 1K. So in that regime, right, so since we're saying omega is less than 1K, right, HS can be approximated by 100, 1K, omega in comparison to 1K is considered to be 0, right? 100, those cancel. We have 100. We take the log of 20 times the log of that, and we get 40 dB. Right, there's no omega in here, so it doesn't change with frequency, right? So it's just a 40 dB line with no slope. All right. Now, when omega is greater than 1K, HS can be approximated by, and the numerator, yeah, in this example, the numerator is always real, it never changes, right? But now we have S plus 0. Since S is so much bigger than 1K, it's effectively 0, right? These are asymptotic plots, right? And this is approximately, right? So when we take the square, so when we find the magnitude of that, right, we take the absolute value, right? That's the magnitude. We have this. And we have that relationship. All right. So let's put that into our log. That's 10 squared, right? So 10 squared, 1K squared, omega squared, we can turn that into 40. Log 10, 1K omega, right? And that gives us a minus 40 dB slope. Right? So that's minus 4 dB per decade, and it equals 0 dB when omega equals 10K. All right. And
do you always
maybe
want omega in the numerator? Is that why you flip that over?
it's best to do the magnitude plot while it's fresh in our minds. All right. So magnitude less than 1K is 40 dB. Straight line. Right? Magnitude now, I had said that it's 0 dB at 10K, which is here, right? But another way, and then you could draw your line from there. But really, you could start your line here, right? Because you know that's the breakpoint, 1,000, and go and do your 40 dB per decade slope. Making sure that instead of, so anyway, we go over 1 decade and we go down 40, right? And we can highlight the important bit. Now, when you're kind of sketching this on an exam, like what do we really need to know, right? Well, I need this point here, right? I need the fact that the gain was 40 dB. I need this to happen at that frequency. And then all you have to do is just say minus 40 dB per decade. So really, like an abstract painting, I'm going to shoot like what is the minimal thing that gives truth, right? There's 40 dB, happens at here. That's it. I mean, this is fancier, but really the fact that the breakpoint is here, the slope is here, that tells me it's a second order system. Tells me that it's repeated roots, and it tells me it has a gain of 40 dB. Shows that it's a low pass filter. So I don't, now what this doesn't tell me is whether it's inverting or non-inverting, right? Because the magnitude loses the phase information, and the phase loses the magnitude. But with the phase information, then you can tell what it is. So let's go back and do phase. So for phase, we have omega less than 1K, omega is equal to 1 kiloradient per second, and we have omega greater than 1K. Now, HS equals 100 times 1K squared, right? Which is 100 times 1K squared at an angle of 0. There's no omega term in this. So this, no matter what, for the rest of these kinds of low pass filters, the phase of the numerator will always be 0. And I don't necessarily care about the magnitude because I've already done that, right? Now what I want to know is the phase of the denominator. So that's really all I have to worry about. So when omega is less than 1K, right? This is so much bigger than that. So I'm just saying this is the denominator, right? I get 1K, right? This is all real. There's no imaginary. So the phase is 0, right? So, you know, the phase of the numerator minus the phase of the denominator equals the total phase, right? So we have 0 minus 0. So we have, excuse me, 0 degrees phase. Okay, well, I'm just going to change colors here so we can keep track. Well, now the denominator, when they're equal to each other, it's going to be 1K plus 1KJ times 1K plus 1KJ, right? And that's really what? 1K square root of 2, 45. But remember, we don't really care about the magnitudes at this point. We've already calculated it, right? It's really just these two phases. So the phase of the denominator when omega equals omega naught, in this example, it's, right, it's 90. So the phase total is 0 minus 90 equals minus 90. Okay. Now when omega is greater than 1K, again, the numerator doesn't change for this example. It's all in the denominator. And this can be approximated by S squared because omega is so much bigger than omega naught that it drops out. So that's really J omega times J omega, which is really omega 90 degrees times omega 90 degrees. Again, we don't really care, right, about the magnitudes at this point. So the phase of the denominator is 180. So the total phase is minus 180. Now we really have one repeated pole at 1,000. So we just there's our 1,000. We need to go a tenth. We need to go a hundredth. So that gives us our points, right? When we're below a tenth of the pole, right, it's going to be 0. When we're at the pole, we're minus 90. And when we're 100 times greater than the pole, we're at minus 180. And there you have it. Now, for the exam, right, I got to have here that midpoint. I need those values, right? 0, minus 90, minus 180, right? And I need it to change here. I need that value shown and that value shown. But you also have to show that it's flat and then changes, right? And that then it flattens out, all right? So you need to show this curve, flat, slope, negative slope, flat. It changes here. It's still it's going through minus 90, and then it changes there. And so, yeah, in a similar vein, omega naught divided by 10, omega naught, 100 omega naught, 0, minus 90, minus 180. That pretty much gives me everything I need to see.
There, could you just go over why you flipped over when you were taking the magnitude? You flipped over the fraction and made it a negative 40 dB. Just wasn't sure why we did that.
So we pretty much have the same problem as before, except the capacitances are different. All right. We have, and I'm just going to label them equals 1,000, right? So this was a low pass filter, right? And it had the form multiply these together to get the total response. That's still what it was before. And that's our new transfer function. All right. And all's it, you know, we just had to remember a few things, right? Our inverting configuration, and then how to do impedances in parallel, right? And taking that ratio and then just, you know, working it out, right? So for the magnitude, we're going to have omega less than omega 1. We're going to have a point in between where omega is in between the two poles. And then we're going to have a spot where it's larger than both the poles. Okay, so if omega is less than 10, it's also less than 1,000. So we're left with 10, we're left with 1,000. Cancel. I take the log, 20 times the log of 100, and I get 40 dB. There's no frequency component, so it's just a straight line. Now, when we're in between, all right, S is greater than 10, right? But it's less than 1,000. So the omega is greater than the 10, so the omega stays, but it's less than the 1,000, so that drops out. Okay. The second pole drops out, and we're left with
drops out.
right, that when we take the magnitude of that and put it into our dB form, right, we get minus 20 dB per decade slope, and it's 0 dB when omega equals 1,000. Okay. Now, when omega is greater than the highest pole, right? So that means S is greater than that, S is greater than that. We're left with okay. This becomes okay. Okay. So now when we take the magnitude of that, becomes 1,000 squared divided mega squared. Okay, we take out the square root, and then we put it in terms of omega, not 1 over omega. And we have that slope. Now so it's 40 dB per decade. Now really, we start off at 40 dB, right? We just draw that kind of straight across. Now you can try to find where something will be equal to 0 dB and then do the slope, but really go to the first pole, the first breakpoint, which is here, right? And that is so from here, it's going to go down 20 dB per decade. Okay. And then rather than try to calculate where that line should be, just go to the next breakpoint here and know that it's going to be 40 dB per decade. So rather than here, it's there. And then what we can do is just highlight the complete response. What do you need to know? Or what, that it's 40 dB here. There's a breakpoint. You can even just say minus 20, right? I get what you're saying, but it's 20 dB per decade. Here it's minus 40 dB per decade, right? It has that breakpoint, and it has that breakpoint. This doesn't change, right? This is the numerator. There's no frequency dependence. So the phase of the numerator is going to be 0 under all these cases. All right. So now, D of S will be approximately zero J plus 10, 0J plus 10, 1,000. That's all real. That's all real. 0 plus 0. All right. just slightly change colors here. When omega is equal to omega naught, right, we have 10J plus 10, right? This is still going to be 0J plus 1,000, right? So that's still going to be 0 degrees phase. And here we're going to have 45, 0 minus 45, we're going to have minus 45. I'm going to skip to here. The first root, it's all J omega now because omega is a lot bigger than the first pole, right? But now we're at 1kj plus 1k. Ignoring the magnitude, that's 90 times minus, that gives 45. Again, ignoring the magnitudes, 135, right? Phase total is phase numerator minus phase denominator is minus 135. Here, right, it's really J omega plus 0, J omega plus 0, because omega is so much bigger than either pole, right, that we're assuming that it's going to drop out, right, because it's asymptotic. So that means we have J omega just becomes omega 90. This becomes omega 90 as well. We're ignoring the magnitudes, right? We combine these. Phase total equals 0 minus 180 equals 180. So we have a pole at 10. We have a pole at 1,000. That means we have to go 10 below and 10 above the first pole, and that means we have to go 10 below, which just so happens to be the above, and here. And here the phase was supposed to be 0. At the pole, it was going to be 45. In between, it was going to be 90. Then it was going to be 135, and here. And then it flattens. So we've done a non-inverting integrator. We've done a low-pass filter, non-inverting, even though it was made out of two inverting stages with repeated poles. And we've done a low-pass filter with two separate poles. In this exam, we're not going to do complex poles. All right? Every pole and every root will be real. Now, we have done examples of high-pass filters, right? Or I have examples in my case studies, right? But, right, I would just have some gain and some pole and some slope, right? And the phase would come, you know, it'd start off at, if it was second order, 180 down to 0, 90. This would be 40 dB up, right? And then if we had two separated poles, right, I'd have something sharp, something a little less sharp here, and then the so let's say you're having a hard time drawing this, right? All I need to do is, let's say it was 10, that's 1,000, 40, 20, and whatever gain it happened to be. Here would just be 180 down to 0. And this would be 10 divided by 10, right? And this would be 1,000 times 10, right? So even if you're messing it up, really, you can just say where the breakpoints are. So if you're stressing out about drawing it on grid paper, you don't really have to. All right. Now, what I want to do for the rest of class is to go into breakout rooms, and then you're going to work on an assignment together, which is in Canvas. And you can either go through assignments and click on Module 8 in class activity, or you can go to the modules. And click on the in-class activity, all right? And you just click on load that in. Now, everybody should do it, right? And everyone will have a slightly different question, but I'm gonna break you up into breakout rooms of 4 so that you can help each other. But you can do this assignment as many times as you want until you get it right. And if you're listening to this because you couldn't come to class, you can do it on your own or you can do it with friends. The due date is effectively for these in-class assignments the end of the semester, right? Right before the final exam begins, that's when all these assignments you can no longer do. But this particular question, it would be very similar to question 1 on the midterm. And you get a plot and you have to basically type in the function in terms of delta functions, step functions, or ramp functions. So like if you thought there was a delta function, right, you'd see delta t, right? And then if you thought there was a delayed step function, you'd say u minus t minus 1. Let's say it was 1. And then, you know, if you thought there was a scale factor to it, you know, times a ramp function. Okay. Syntax is okay. I submit it. That's totally wrong, which I knew. I didn't want to give away the answer. Okay. But you can keep doing that one until you get it right. So, the breakout rooms will randomly assign you, and I'm going to stop recording for that. Okay.
Oh, wait, you're still doing it?
Okay, I'm going to open all rooms. So you should have received an invitation. Leave this and go to the other and start working. Okay.
Hey, Professor, I had a quick question.
Oh, he's not even here.
I was trying to talk to him, but he dipped.
Oh, like he just left the whole meeting?
Yeah, I guess I started talking to him, and then like his name disappeared.
Oh, he might have gone into one of the breakout rooms because someone probably asked a question.
Yeah, maybe.
I'm just wondering if we can leave the meeting already.
Oh yeah, I mean class is over.
Yeah. All right, well, I'm gonna dip then.
Professor's not here, so I guess we're done.
All right, see you guys.
Peace.
Peace.